Hello everyone, welcome to the compiler design series. Today we are going to study about LR0 parsing with numericals of LR1 parser and SLR1 parsers.
Talking about LR parsers. As the name suggests, LR parsers parse the string from left to right. That is bottom-up parsing. Bottom-up parsing is followed in LR parsers, which is divided into four classes of parsers: LR0 parser, then SLR1 parser, that is simple LR, then LALR1, which is look ahead LR, then CLR1, which is canonical LR. LR0 and SLR1 both contain LR0 items. LALR1, CLR1 both contain LR1 items. An LR0 parser is bottom-up parser, which, as the name indicates, parses the string from left to right. First step is to number the productions. The given grammar is S derives A derives small a capital A, and A derives B. We want to number this grammar in the order it appears. That is, S derives A will be first, A derives small a capital A will be second, and A derives B will be third. The second step is to write augmented grammar. So the basic step will be to write S dash derives dot S. Augmented grammar will contain the start symbol of your grammar. In this case, S. So we will write S dash derives dot S and the dot here. Let me explain this via working of parser. The dot here acts as a pointer. That is, everything on the right hand side of the dot is not seen by the parser. And everything that is on the left hand side of the dot, it has been seen by the parser. Here it means that the parser is yet to see anything because S is a start symbol. And if it has not even seen the start symbol, the parsing hasn't even begun. So we write all the productions in the same manner, that is S dash derives dot S. So we write S derives dot AA. The dot has to be in the front, that is extreme left of the RHS. Again we write the production A derives dot AA and A derives dot B with dot in the extreme left of RHS. So if you look at this new grammar, this is what we call an LR0 item. An LR0 item contains dot after it. In layman's language, an LR0 item is something that contains a pointer or a dot. The third step is to write canonical collections. A canonical collection is a valid number of states for an LR0 parser. As it must explain, we are going to draw an automata now. So now if you want to write a canonical collection, you have to give a state 0 for the automata. So the first step to write a canonical collection is to take closure starting from augmented grammar. The augmented grammar is S dash derives dot S. So what does it mean to take a closure of anything? You look at this dot here. The right hand side of the dot contains a non-terminal S. So we will write all the productions of S where the right hand side of the production begins with dot in the start. Therefore, we write S derives dot AA. Again, the dot in this production is before a non-terminal A. So we write all the productions of A, that is A derives dot AA, where dot is in the start. And we write A derives dot B, where dot is in the start. Now look at the new productions of A that we just wrote. The dot is not before any non-terminal, therefore the closure will stop here. This is going to be the first state of our grammar, that is state I0. From this, we are going to derive new states. The question comes here that how do we know what's going to be the input? How do we know what grammar will be used for the input? Hang on. Now carefully look at state I0. On the right hand side of every production, we have a dot. Every non-terminal or terminal after dot is going to be the input. That is, for first production, S dash derives dot S, the input will be S. For second production, S dash derives dot AA, the input will be capital A because it is after dot. For third production, A derives dot small a capital A, the input will be small a. And for fourth production, A derives dot B, the input will be non-terminal B. So why do we take an input and what happens after we take an input? So state I0 on input S gives a new state, S dash derives S dot. So what happened here? Whenever you give an input, be it a terminal or non-terminal, the dot moves to right by one position. That is, we gave input S. So only the production that had S after the dot will be used. In this case, S dash derives dot S. So S was present after dot only in one production rule, that is S dash derives dot S. So we will use only that production. And after we give input S, the dot will move one position to the right. That is, we get S dash derives S dot. You see here the dot is in the extreme right of the right hand side. So it will become a final state. So what does this production mean? It means that the parser has seen everything of the start symbol. That is, it has stopped parsing. Now for the second input, that is input A. On input capital A, there is only one grammar that we can use. It is sderives.aa. So after using input A, the grammar we will get is sderives a.a. What happened? After input A, the dot shifted one position to the right. So now if you look at the production, the dot is before a non-terminal which is A. So we have to write closure of A. The closure of A will contain all of its production rules with dot in the front, that is aderives.aa and aderives.b. This is going to be a non-final state because the dot is not in the extreme right of the production rules. So it will look something like this. So for state I0 on input small a, the grammar we will use is a derives dot a capital A. On input A, it will become a derives a dot a. The dot has shifted one position to the right. There is a non-terminal after dot, therefore we will write all the productions of that non-terminal. That is A. So we write a derives dot aa and a derives dot b. Again, this is a non-final state and it will look something like this. The next production we will look at is a derives.b. So the input will be used as b because it is after dot. So after the input b, it becomes a derives b dot. Why? Because the dot shifted one position to the right. Again you see that the dot is in the extreme right of the production, so it becomes final state. The diagram will look something like this. Now again, if you look at I2, we can still parse the grammar. Now one of the important things. Most of the time it happens that when you are solving questions with your friends, most of you end up naming different states with a different name. So I would recommend that you start writing states in the order of the appearance of their grammar. For example, in state I0, the grammar s dash derives dot s appears first. We drew the state I1 on input s. Again, the second production rule of I0 was s derives dot aa. So we used this production and derived whatever state we could and named it I2. We took the third production rule, derived whatever state we could from input A and named it I3. Similarly, we derived state I4 from I0. So now in this order, we are going to find more states starting from state I2. So if you look at state I2, we will take inputs of capital A, small a and b. Why? Because the dot is before these terminals and non-terminals. Therefore, let us consider a grammar that says s derives a dot a. So after input of capital A, the grammar will become s derives aa dot. Again, this is a final state because there is nothing on the right of the dot. The next production rule is a derives dot aa. So the input will be small a and it will look like a derives a dot a. The dot will shift one position to the right. The dot is before a non-terminal, therefore we will take closure of it and write all its production rules with dot in the very beginning. Therefore, a derives dot aa and a derives dot b. We have seen this grammar beforehand in the state I3. Therefore, we will draw a curve that transitions I2 to I3 on input A. We will not repeat any state that we have seen. So, if you derive a grammar that is similar to a grammar in previous state, we will go back to the previous state. Now, I2 on input B, the grammar we will use is a derives dot b. So, a derives dot b becomes a derives b dot. What happens is the dot shifts one position to the right. Again notice that this is going to be a final state because the dot is in extreme right. We have seen this grammar before in state I4, so we will not repeat the state and write state I4 in its place. Now about state I3. Look at the grammar a derives dot aa. This grammar is going to give us a recurring state, that is a derives dot aa will become a derives a dot a on input small a, and the dot is before a non-terminal, therefore we write all the productions of non-terminal, that is all the productions of non-terminal a. So a derives dot aa and a derives dot b. So we have seen this before, it is state I3 itself, so I3 on input a goes back to itself. Again, a derives dot b, we have seen this production before, it's going to yield the state I4. How? A derives dot b on input b will become a derives b dot. We will not write this state again because we have already seen it. So I3 on input b transitions to state I4. Now the grammar a derives a dot a. So this grammar is going to become a final state if we give input capital A. So it becomes a derives aa dot. Again the dot is in the extreme right, so it becomes a final state. We have not seen this state before, so we are going to name it state I6. So this is how we create canonical collections or LR0 parsing automata. The fourth step to find if a grammar is LR0 is to create its parsing table. On the screen, I have the automata that we just created, the numbered grammar along with a new table. So if you focus on the table, you will see three main columns, which is states, action and goto. The column of states corresponds to the number of states in the automata. Starting from I0 to I6, we have 7 states. So we write it all in the column of states. The action table contains all the transitions from terminals and the go-to table contains transitions from the non-terminals. Now you might be wondering that the action table contains AB because it is in the grammar, but why dollar? If you look at the state of I1 in the automata, you will see that this grammar does not belong to the original grammar. Why do we have to have it in the automata? This is because whenever a parser wants to finish parsing, be it any condition, we have to have a state it can safely go and terminate the parsing action. So dollar will be standing for that. There are scenarios when end of a string is determined by the presence of dollar. So if there is dollar in the end, the string will terminate. So dollar stands for termination of parsing. Back to the go-to column, it contains all the non-terminals in the grammar, that is A and S. So to fill this table, we are going to study two new concepts, which is going to be a shift move and a reduce move. So what is a shift move? If a non-final state transitions on a terminal to another state, then it's going to be a shift move. Now look at state I0. On terminal A, it goes to state I3. So we write S3 in the column of A. S is a shift move. 3 is the corresponding number of state that the input leads to. That is state I3. On input B, state I0 goes to state I4. So we write S4. Why S4? S4 is a shift move because I0 is not a final state and it leads to another state via non-terminal B. So we are going to write S4 where the 4 corresponds to I4. There is no transition on dollar. On input capital A, I0 goes to I2. So we write corresponding state number 2 under the column of A, and on non-terminal S, I0 goes to state I1. Therefore, we write corresponding number 1. Now talking about state I1, it is not the part of original grammar. It is an augmented grammar. So what we are going to do, we are going to accept all the states where parser can terminate. So under the column of dollar, we are going to write accept. Now talking about state I2, I2 on input small a goes to I3. So we write shift 3. That is, it shifts to state I3. Therefore, S3. Again, I2 on terminal B goes to I4. That is shift 4, S4. There is no action on dollar. On input capital A, I2 goes to I5. Therefore, we write corresponding number 5. There is no action on non-terminal S. State I3 on terminal A goes to I3. Therefore, we write S3, that is the shift move, and 3 is the corresponding number of state it led to. Again, on input B, state I3 goes to state I4. Therefore, we write S4. By non-terminal A, state I3 goes to state I6. Therefore, we write corresponding number 6 under the column of A. Now, for state I4, I4 is a final state. Also, it is a part of our grammar. We are going to study about something called reduced move here. If there is a final state, then its action columns will contain reduced move corresponding to the number of grammar it contains. Look at all the final states in this automata except I1. Because I1 is augmented grammar, we are going to look at the real grammar. That is I5, I6 and I4. All of them contain the real grammars. We are going to write R with the corresponding number of grammar we numbered. That is S derives AA number 1, A derives AA number 2 and A derives B as number 3. So if you look at R4, A derives B is the third grammar. So we will write R3 in the entire row of state I4 except the go-to part of the table. Similarly for I5, I5 is the final state which contains grammar number 1. So we are going to write reduced move for it, that is R1 in the entire row except the go-to part. For I6, it is also a final state and it contains grammar number 2, that is A derives dot AA. Therefore, we will write reduced move in the entire row of state R6, that is R2 except the go-to part. We are finished with creating a parsing table. Make an important observation to check if there are multiple entries in the table. For this one, there are no multiple entries, therefore, this grammar is going to be LR0 grammar. But wait a second, I said there is going to be 5 steps. So if we are able to conclude LR0 grammar in 4th step, then why do we need a 5th one? It's an important step for you to know about conflicts in the parser. The 5th step to find if a grammar is LR0 is to check for parser conflicts. Checking for conflicts is an efficient method to identify if the grammar is not LR0 in the 3rd step while you are creating the canonical states. So there are 2 types of parser conflicts. First one is RR, that is reduce conflicts. Look at the grammar we have. A derives alpha dot and B derives gamma dot. Both of them are reduced productions and they will yield a final state. But if both of them are in final state, then there will be multiple entries to record them in the parsing table. This will cause ambiguity to the compiler because compiler won't know which reduced move to carry on. Similarly, the second conflict is shift-reduce conflict. Let us say that there is a grammar A derives alpha dot AB and B derives gamma dot. Here we have shift move as well as reduced move. The parser will not be able to define if it's going to be a final state or not. So you can check for these conflicts when you're creating the canonical states. Either way, if you don't check for this, you will find multiple entries in the parsing table. So that was how to identify LR0 grammar. Now we are going to study about simple LR1 parser. The process to create SLR1 parsing is same as LR0 as both of them use LR0 items. The difference is seen while constructing the parsing table. In LR0 parser, we write state with reduced grammar in the entire row. But in SLR1, we will write state with reduced grammar in the follow of right hand side. Look at this table. We will only change the entries for final states. Let's find follow of all the non-terminals first. Follow of S is dollar as it is a start symbol. Follow of A will be first of A. In the production of S derives AA and follow of S. That is, the follow of A will be A, B and dollar. The link of video explaining first and follow is in the description box below. Back to the parsing table. State I4 contains A derives B dot, which is the grammar number 3. We will write R3 in the follow of right hand side of the grammar. Follow of A is A, B and dollar. So we write R3 under the columns of A, B and dollar. State I5 contains S derives AA dot. This is grammar number 1. We will write R1 in the follow of right hand side of the grammar, that is follow of S, which is dollar. So we write R1 under dollar. State I6 contains A derives AA dot, which is grammar number 2. So we will write R2 in the follow of right hand side of the grammar. Follow of A is A, B and dollar. Therefore we write R2 under the columns of A, B and dollar. This is the complete parsing table of SLR1 grammar. It does not contain multiple entries and it also does not contain RR and SR conflicts. Hence the grammar is SLR1 grammar. Thank you so much for watching the video. I hope it was helpful. Please like, subscribe, comment and share. Stay tuned for the upcoming videos.